What happens when a massive tunnel-boring machine weighing more than 2,000 tons suddenly becomes trapped deep beneath the majestic snowy mountains? This is not some far-fetched disaster scenario from a movie, but a real nightmare draining billions of dollars from the snowy 2.0 mega project. This is a large-scale pumped storage hydropower project in Australia, built to connect Lake Tantangara and Lake Talbingo, turning the entire mountain into a gigantic energy storage facility. Faced with this construction crisis, how can engineers successfully rescue the trapped machine and continue excavating 27 kilometers of tunnels to complete the country's largest underground energy battery? Join Mandarin Tech as we journey deep underground, uncover each layer of the structure, and decode the most extreme construction challenges of this historic mega project in today's video. As Australia increasingly relies on wind and solar power, electricity generation can exceed demand during off-peak hours but fall short when consumption rises. For this reason, the country is investing approximately 12 billion Australian dollars to build Snowy 2.0, which will store this surplus electricity and return it to the grid when it is needed most. The project uses the Tantangara and Talbingo reservoirs, located at different elevations, and connects them to a power station hidden deep within the snowy mountains. Surplus electricity will be used to pump water to the upper reservoir. When the grid requires additional capacity, the water will be released downhill, driving 6 generating units before returning to Talbingo. With a designed capacity of 2,200 megawatts, Snowy 2.0 is expected to become a vast energy storage facility capable of supplying electricity to around 3 million households for an entire week, while helping Australia's power grid remain stable even when the wind stops blowing and the sun disappears. Construction of Snowy 2.0 officially began in early March 2019 when the first crews entered Lobs Hole, a mountainous area with almost no infrastructure capable of supporting such a massive project. Around 26 kilometers of access roads were newly built or upgraded. Excavators removed layers of soil. Bulldozers leveled the terrain, while hard rock was drilled and blasted to widen the roadway. Narrow bends also had to be realigned so that heavy-haul vehicles could transport cutter heads, motors, and components weighing hundreds of tons. In areas with weak ground, slopes were reinforced, while drainage channels and cross-culverts were installed to keep the roads stable after heavy rain. Environmentally and culturally sensitive areas were surveyed, marked, and fenced off before machinery moved in. Once the transport routes were operational, the construction base at Lobs Hole began to take shape, including accommodation facilities, storage yards, power and water systems, and an assembly area for the tunnel-boring machines. This logistics network transformed the isolated mountain region into a gateway, allowing workers, machinery, and thousands of tons of equipment to move deep into the underground construction site of Snowy 2.0. After the Lobs Hole construction base was completed, crews began driving 2 tunnels from the mountainside down to the power station complex deep beneath the snowy mountains. One tunnel would transport workers and equipment, while the other would carry electrical cables and ventilation systems and serve as an emergency escape route. At the main tunnel portal, TBM Lady Eileen Hudson was assembled to excavate the approximately 2.85-kilometer access tunnel from Lobs Hole to the power station area. The machine featured a cutter head more than 11 meters in diameter, followed by its power systems, conveyor belts, and tunnel lining equipment. As the cutter head crushed the rock face, excavated material was carried outside by conveyor belt. After each advance, a mechanical arm assembled curved concrete segments into a complete ring behind the machine. Grout was then injected into the gap between the lining and the surrounding rock to secure the structure. Hydraulic jacks pushed against the newly completed concrete ring, driving the entire machine forward for another cycle. Surveying equipment continuously controlled the excavation direction because even a small deviation could cause the tunnel to miss the power station area. After approximately 2.85 kilometers, Lady Eileen Hudson broke through into the underground complex. From that point, the main access tunnel became the primary route for transporting workers, materials, and equipment deep into the snowy mountains. However, a single access tunnel was not safe enough for a construction site located hundreds of meters beneath the mountain. A fire, rockfall, or accident could completely block the main route. For this reason, the Kirsten tunnel boring machine was assigned to excavate a second underground corridor towards the power station, connected to the main tunnel by multiple cross passages. This tunnel would provide both an emergency escape route and access for rescue teams to reach the affected area. Along the tunnel, crews installed electrical cables, data lines, water supply, firefighting, and drainage systems. Large ventilation ducts carried fresh air deep into the mountain, while high-capacity fans removed rock dust, exhaust gases, and heat. Fire doors at the connecting passages helped prevent smoke and flames from spreading between the two tunnels. In this way, the construction site gained a vital corridor carrying electricity, fresh air, and a safe escape route to the underground power station. After breaking through to the underground power station area, Lady Eileen Hudson was reassigned to excavate an approximately 6-kilometer tunnel connecting the generating complex to Lake Talbingo. Because water will travel in both directions, the tunnel's elevation and gradient must be controlled precisely to minimize energy losses and prevent air pockets and areas of standing water. Ahead of the cutterhead, probe holes help detect fractures, groundwater, and zones of weak rock. When unstable geological conditions are encountered, the construction team must inject grout, manage water ingress, and reinforce the support system before the machine can continue advancing. Behind the machine, curved concrete segments are assembled into sealed lining rings, while the gap between the lining and the surrounding rock is filled with grout to keep the tunnel stable under water pressure. By May 2026, the main excavation had been completed. However, the connecting sections still had to be concreted, sealed, and inspected before water could flow through them. From Lake Tantangara, Florence was assigned to excavate an approximately 15-kilometer headrace tunnel, also the most difficult section of Snowy 2.0. From the outset, the machine encountered soft, wet, and unstable ground. In late 2022, after advancing only about 70 meters, the ground above suddenly collapsed, creating a sinkhole nearly 9 meters deep. The construction team had to control the groundwater, drill investigation holes, and inject cement grout into the voids. Florence was not able to resume operation until nearly a year later. However, in 2024, hard rock and ground pressure once again trapped the machine. Engineers had to use ultra-high-pressure water jets to break away the surrounding rock, creating enough space to free Florence. The machine resumed excavation in July 2024, but the tunnel has still not been connected. To reduce risk and shorten the schedule, the project introduced Monica from the opposite direction. Its components were transported through the access tunnel and assembled inside an underground chamber at Marica. From there, Monica excavates towards Tantangara, while Florence advances from the other end. At the center of Snowy 2.0, the tunnels lead to 2 enormous underground caverns for the power station and transformer hall. Because their dimensions exceed the capabilities of TBMs, construction crews must excavate the rock layer by layer using controlled drilling and blasting. Rows of deep holes are drilled into the rock face. Explosives are arranged according to a precise pattern and then detonated at extremely short intervals, removing sections of the mountain without destabilizing the surrounding area. After each blast, ventilation fans clear the fumes, excavators remove the broken rock, and the newly exposed surfaces are immediately reinforced with steel bolts, mesh, and sprayed concrete. Excavation progresses from the crown downwards, forming the power station cavern, technical galleries, generating unit pits, and connections to the waterway system. At both ends of the project, water intake and outlet structures are being built at Tantangara and Talbingo to connect the 2 reservoirs to the underground tunnel network. Temporary natural rock plugs remain in place until the gates, concrete structures, and tunnels behind them are completed. Deep underground, surge shafts are also excavated to absorb pressure fluctuations and reduce water hammer when the turbines or valves change operating states suddenly. From the main tunnel, water will pass through high-pressure steel pipes to the 6 generating units. This section must withstand the full pressure created by the difference in elevation between the two reservoirs. The pipe sections are lowered into inclined tunnels, aligned, welded, and inspected before grout is injected around them, and they are encased in concrete. Inside the power station cavern, workers continue pouring foundations and installing overhead cranes, cooling systems, firefighting equipment, and control cables, preparing for the testing and commissioning of the turbines, generators, and transformers. The deeper Snowy 2.0 advances into the Snowy Mountains, the further it moves from its original projections. The estimated investment of approximately 6.1 billion Australian dollars approved in 2018 had risen to 12 billion Australian dollars by 2023, while the final cost could still continue to increase. Complex geology, slow tunneling progress, design changes, labor shortages, and rising material prices have delayed the project by several years. The current target is to generate its first electricity in the second half of 2027 and complete all 6 generating units by the end of 2028, but this schedule is still not entirely certain. Controversy also surrounds the construction area within Kosciuszko National Park. Access roads, storage yards, and the enormous volume of excavated rock are placing pressure on the alpine ecosystem. Some of the excavated material may contain acid-forming minerals or naturally occurring asbestos, requiring the project to classify and manage it under strict controls. Connecting the two reservoirs has also raised concerns about invasive fish and pathogens moving between catchments. Snowy 2.0, therefore, stands at the center of a major contradiction. It is being built to support a clean energy future, yet its financial, time, and environmental costs continue to rise. If successful, it will become a strategic energy storage facility for Australia. If cost overruns and delays continue, it could become one of the most expensive lessons in the limitations of megaprojects. If Snowy 2.0 is turning the mountains of Australia into a giant energy battery, then in the United States, Chimney Hollow Reservoir is transforming a Colorado Valley into a strategic water reserve for the future. Located west of the town of Loveland, Colorado, Chimney Hollow Reservoir is a large-scale water infrastructure project developed through a partnership between Barnard Construction and Northern Water, with the participation of 12 water providers across northeastern Colorado. After decades of planning and construction, the project's main dam was completed in 2025, marking an important milestone in the history of modern dam construction in the United States. With a total investment of more than 570 million United States dollars, Chimney Hollow is considered the tallest dam built in the United States in the past 20 years. The project was born out of a geographical paradox in Colorado. Most of the state's population lives east of the Rocky Mountains, while much of its water originates in the west as melting snow. As a result, Chimney Hollow was built as a barrier across a valley, creating a reservoir that can store water and release it gradually over time. It is not merely an artificial lake, but a vital link in a water storage and distribution system designed to serve hundreds of thousands of people for decades to come. Once completed, Chimney Hollow will do more than simply add another reservoir to Colorado. It will also change how the Front Range manages its water resources in the future. The Chimney Hollow Reservoir provides additional storage capacity when water supplies are abundant and allows that water to be redistributed when demand increases. Rather than allowing water to move through the system passively, the project gives water providers greater control over when water is stored, when it is released, and how much water is delivered to each area. From an engineering perspective, Chimney Hollow is also a representative example of modern water infrastructure. However, the project demonstrates that building water infrastructure in the 21st century is no longer simply a matter of concrete, rock, and machinery. The issue of naturally occurring uranium in the granite serves as a reminder that every major project must confront its own geological and environmental challenges. As a result, the true significance of Chimney Hollow lies not only in its ability to store water, but also in how people monitor, adapt to, and operate the facility safely before that water is delivered to the community. If Chimney Hollow is the story of how the United States is storing water for the future, then Rogun Dam is Tajikistan's effort to harness the power of the Vaksh River to generate electricity for millions of people. Chimney Hollow is steadily demonstrating that the greatest challenge is not always creating new water supplies, but finding effective ways to store and manage the water that already exists. What makes this reservoir especially remarkable is that it was not formed by a natural river. It was created through engineering, topographic planning, and a complex water management system designed to deliver water precisely where it needs to be stored. In your opinion, should water-stressed cities continue building massive reservoirs in the future, or should they prioritize water conservation and reuse strategies instead? Let us know in the comments below, and don't forget to subscribe to Mandarin Tech for more fascinating engineering projects from around the world.